Hi, I'm Bob. Welcome back to the tutorial on the exercises and application for the textbook Econometric Analysis, the 8th edition by Professor William Greene. Today, we will solve exercises 7 to 9 at the end of Chapter 3, the Squares Regression. Exercise 7 is about the demand system estimation. The expenditure on each category depends on total income, the price of the good, and other goods prices. Income Y is defined as the sum of the expenditures on the three categories. We need to prove that the sum of the betas is 1 and the sum of the other 4 columns is 0. We write the expenditure on consumer durables in matrix form. It is first written in elements. It can also be expressed using vector notation. Denote an explanatory variable matrix X, and the equation can be written as ED equals X times beta D plus epsilon D. The OLS estimator vector is BD. Similarly, the OLS estimators for non-durables and services are as follows. Note that the explanatory variable matrix X is the same for the three categories. The three goods in the demand system share the same explanatory variable matrix, but different outcome variable vectors. The sum of the three OLS estimators is as follows. By definition, the sum of the expenditures on the three categories is the total income Y. Now we see a familiar expression. It is the OLS estimator from the regression of Y on X. The explanatory variable matrix X contains the vector Y, so it is a perfect fit. The estimated coefficient on Y is 1, and those on the other 4 columns of explanatory variables are 0. The coefficient on Y is the sum of the three expenditure coefficients. Thus, we prove the result. Next, let's see exercise 8. It is about theorem 3.7 in the textbook. It states that if the square of the t statistic on a variable in the multiple regression is less than 1, then the adjusted R² will rise when that variable is deleted from the regression. It is too difficult for me to solve it mathematically. I want to skip this problem and only show you the conclusion in Stata. Please download the dataset from the link below. Here's the regression model for US workers' wages. We regress the workers' log wage on schooling, marital status, age, gender, number of children, and parents' household income. The t statistic for the coefficient of the number of children is minus 0.23. Its square is below 1. The adjusted R² for the regression is 0.2665. According to theorem 3.7, the adjusted R² will rise if we drop the number of children variable. And it is true. The new adjusted R² becomes 0.2667. Note that the adjusted R² has been adjusted by the degrees of freedom. If we look at the R-squared, it will always decrease when explanatory variables are dropped from the model. The command eReturnList can help us compare the usual R-squared. We can also verify that the adjusted R-squared falls when we drop a variable from the regression if the squared of the t-statistic on that variable in the multiple regression is greater than 1, such as the variable schooling. The adjusted R-squared falls to 0.1677 after we delete schooling. The if eSample modifier makes the models we compare have the same sample size. Let's turn to exercise 9. We will compare the R-squared between regressions with and without a constant term. We can use matrix algebra to show the result. First, we look at how the R-squared is computed. Write the regression model y equals x times b plus e. The total sum of squares can be decomposed as the regression sum of squares plus the error sum of squares. It is the notation in William Greene's textbook. In Jeffrey Woodridge's textbook, the total sum of squares is written as the explained sum of squares plus the residual sum of squares. They use different names for the same decomposition equation. Then the goodness of fit measure, R-squared, is defined as the ratio of the regression sum of squares to the total sum of squares, or 1 minus the ratio of the error sum of squares to the total sum of squares. Using the residual maker M0, we can write the R-squared in terms of M0, residual column vector E, and outcome variable column vector Y. For a regression with a constant, we can further simplify it because residuals have zero mean. M0 times residual is the deviation term of residuals, so M0 times E equals E. For a regression without a constant, the R-squared equals 1 minus the ratio of the error sum of squares to the total sum of squares, and they are not in deviation terms. Now, we only need to compare the two denominators. By writing the residual maker M0 out, we can reach the answer. The last step is because I prime times y is a scalar. The answer shows that the R-squared in the regression without a constant is higher than that with a constant. We can check this answer in Stata. Using the same dataset, we regress the log wage on schooling with and without a constant. The R-squared is much higher in the no constant regression. Thank you very much for watching this video and doing the exercises with me. See you soon on the following exercises. Take care. Thank you for watching this video and subscribing to my YouTube channel. See you next time.